Me. Hello, everyone. My name is Mohammed Walid Minsha. I'm the president of the ECSE Graduate Student Council. I have with me some of my graduate student colleagues and members from the Graduate Student Council as well. And we would quickly give you an overview of some of the diverse research that we're doing in the department. So we would start with my colleague Megan. Megan, take it away.
Okay. Hi, I'm Megan Podlaski. I work in electrified aircraft modeling and simulation and system identification for like traditional power systems. So the one big project I work on is called Cheetah, which is a cryogenic fully electrified aircraft project that we are working on. It's a whole project that we are working on in conjunction with a few other universities and industry groups. The part that we're working on at RPI is with the modeling and simulation stuff. So we're looking at designing all of the cryogenically cooled components, the electrical system, the thermal system, mechanical system, and control system, and trying to collaborate with the other groups in the project to make sure that their research work is being translated into models that we can then study to the different types of configurations, operational modes, and stuff like that in the aircraft. So I've got an overview of how the aircraft would work. We have like liquid hydrogen storage and different fuel cells, all of the cryogenically cooled transmission lines and bus bars going to the motors. So the way that this project works at the power system that we've developed, we have fuel cells that are going to power a series of motors to propel the plane. And it is being transported from these fuel cells in battery systems via cryogenically cooled components. So we're building up these liquid hydrogen fuel cells alongside the newest fuel cell research. So we have to work with all the groups there to make sure that all of the new fuel cell research is being modeled and simulated properly. And we're also working alongside them to build off of the basis of what we have right now for fuel cells. We're also working with novel superconducting machines. These machines are similar. We're using standard synchronous machines as our basics, but they have different types of losses and structures from conventional machines. And then we also have novel cryogenic transmission lines. These have a different behavior than conventional lines and bus bars. They're operating at 20 Kelvin, so they have a standard structure to like a coaxial cable, but the current and voltage losses are much more nonlinear than a standard coaxial or pi line transmission line. So instead of just performing conventional power systems analysis with these models that we're building, we get to think outside of the box to determine how we're going to protect the system, identify points of most vulnerable to failure, and then transform all of the theory that's being done on the physics side for all of this cryogenic operation and novel components into applied engineering. And then I also work with electrical vertical takeoff and landing modeling and visualization for that. So I've been working on developing an open source library to make multiple domain drone and eVTOL models. So what I've been doing is I've been modeling the electrical, mechanical, aerodynamic behaviors of traditional drones and all of their controls that dictate their behavior. All of these models are equation based to reflect the physics in each component in the system. And then we're doing this to be able to export these into virtual reality simulations as well. Okay, that's all I've got.
Thanks. Yeah, so for this modeling, you use that tool. I think Professor Manfredi introduced that once, Modelica or something.
Yep.
Cool, cool. Yeah, so the current graduate students as well, if you have any questions for any of the speakers, I know this might be one of the first times that we're also looking at each other's research work. So if you're just curious about anything, just feel free to ask. Or if you want to put it in the chat as well, then we can ask that as well. So thanks, Megan. Interesting.
Thanks.
John, do you want to introduce your research? And to the speakers as well, once you start, please mention your research advisors as well for the benefit of the accepted students as well, so they know which group you belong to.
Okay. Hi, everyone. My name is John Rollinson. I'm a first year PhD student. I recently completed my master's at RPI. Um, I work under Dr. Mona Hella in the high frequency integrated circuits group, and my focus is in photonic integrated circuit design for high frequency applications. So, So first, I want to talk a little bit about exactly what electro-optic devices are. So in electrical engineering, there is, of course, the obvious trend of we're always trying to push electrical devices to higher and higher frequencies. And in recent years, that has led to, especially in silicon devices, um, resorting to a lot more advanced device design or sort of exotic techniques for pushing the frequency higher and higher. So one alternative method that we can look at is looking at photonic systems and also alternative material systems for essentially overcoming some of the frequency limitations that we face with traditional electronic devices and especially silicon integrated circuits. Um, so the basic idea for electro-optic devices is an electro-optic material is a material in which an incident electric field applied to the crystal will modulate the polarization of that material and effectively control the anisotropy of the material. So by electrically controlling the polarization of the material, we're then able to electrically control um, essentially an optical beam that we pass through that material. So we can use an electro-optic material to modulate a light source, essentially. So we can do a lot of interesting things with this effect. So we can modulate the phase, polarization, or amplitude of light. Sorry, there's a little typo there. Um, and really, the frequency of operation is limited only by the material parameters of the material that we're using. So really the absorption limits of the materials, which are typically in the range of several terahertz. We can also do more interesting things with these materials, specifically nonlinear optical effects, things like second harmonic generation, four-wave mixing, really more sort of advanced physical concepts that I won't really talk about too much today. So the main applications of these electro-optic devices are really where we have some sort of application where we want to map information from the electrical domain to the optical domain to either manipulate that information or transmit that information. For example, in the application of telecommunications, this is really probably the single biggest application of electro-optic devices is for inline fiber modulators for telecommunications. This is basically how all fiber optic communication is done through the modulation of, say, the amplitude or the phase of an optical beam in the fiber optic cable. But we can also use it for other applications. We can make free space electric field sensors. So an electric field propagating through space will modulate light in the electro-optic sensor, and then from that modulation of the light, we can infer information about the free space electric field. We can do other things like optical frequency comb generation, which is useful for optical metrology or generating supercontinuum optical sources. Um, we can do second harmonic generation, which is essentially doubling the frequency of an optical beam. So we can shoot a laser through an electro-optic material, and by engineering the polarization of that electro-optic material, we can actually double the frequency of the light. So one specific electro-optic platform that we're interested in is called thin film lithium niobate. Lithium niobate is probably one of the, if not the most widely used electro-optic material, simply because it's relatively easy to grow, and it has a very high electro-optic coefficient, so we can achieve very good modulation strength easily. It also has a very large bandwidth, typically greater than 1 terahertz, depending on the device design. And specifically, the platform that we're interested in is lithium niobate on insulator. Essentially, if you're familiar with silicon on insulator technology, lithium niobate on insulator technology is created in a very similar process, where it's essentially the same as a smart cut process, where we end up with a very thin film of lithium niobate on top of most typically silicon dioxide, and then on top of either another lithium niobate wafer or a silicon substrate wafer. So the real advantage of this thin film technology is that we can have greater control over the optical properties of the lithium niobate. So we can control the effective index of the lithium niobate in a thin film version better than we could in the bulk version. We can also eliminate some non-ideal characteristics of the lithium niobate, such as like mechanical absorption modes. Um, and most importantly, we can create integrated photonic devices using lithium niobate. So in the lower right hand corner here, this is a an integrated Mach-Zehner interferometer or a Mach-Zehner modulator. And this is what's used to do amplitude modulation of an optical beam. So in those inline fiber modulators, this is actually the device that's in there modulating the amplitude of the light. So I just wanted to highlight one recent work that we did using this platform. This was funded by the Department of Energy, and we worked with a company out of California, Partau Technologies, and they did all the device fabrication for us. The general application that we were looking at was, can we repurpose thin film lithium niobate Mach-Zehner modulators, which are typically used for telecommunications, as I said. Could we repurpose these devices and use them for very high frequency electric field sensing? So the general idea is that a free space electric field incident on the Mach-Zehner modulator will produce an amplitude modulation in the incident light beam or the light beam passing through that modulator. And then that modulation produces optical sidebands, like you would see in like your communication systems course. And then we can measure these optical sidebands using an optical spectrum analyzer, which is a relatively inexpensive piece of equipment. And then from this sideband spectra, we can then, through say like an inverse Fourier transform, we can actually reconstruct the temporal signal of that incident electric field. So for this specific sensor that we had fabricated and characterized, you can see it in the lower right-hand corner here. This is about 6 millimeters long, to give you a sense of scale. For this device, which was fabricated, we characterized the device to have a negative 12 dBm noise floor, or detection threshold rather, and an extrapolated bandwidth of 150 gigahertz. So the types of applications that we're looking at for this device are really environments where you can't use traditional electrical sensing techniques. For example, in particle accelerators, they have very stringent requirements about the ways in which you can integrate sensors and whatnot. But they need to be able to say sense the bunch length of an accelerated particle. So that would be one application of this type of device. And then this work was also recently published in the Journal of the Optical Society of America, and the publication information is in the lower corner here. Okay, so that's all I have. Thank you for your attention and time. I think you're muted, Waleed.
Thanks, John. Yeah, I had a quick question. So the device that you're talking about, like when it's operating in the modulator mode, can you do the inverse phenomena, use the modulator as a demodulator as well, in which we're using, I guess you're pretty much doing the same
Yeah.
thing in which you have. light and you
Yeah.
wanted to.
Yeah, the effect basically only works in one direction. So you can generate modulation in an optical signal using an electrical signal, but you can't use the modulation of an optical signal to generate or to sort of pick up the electrical modulation. So unfortunately, it only works from electrical to optical. To convert
I see.
from optical back to electrical, you need something like a photodetector um, to sense the signal.
I see. And then what kind of transitions do you have when going from the fiber to this lithium niobate?
So basically, what it uses is a. I'll just try to reshare my screen quickly.
You are muted.
Yeah, he's not muted, but we lost the audio. John, we lost the audio. Can you hear me? No.
No, it seems that somehow he's
Okay.
yeah.
So anyone else has any question for John?
Mm,
Nope. Okay. I guess thanks, John. Kimberly, do you want to go ahead and share your screens?
All right. So I'm
Yeah,
going to
you can
present my
share screen.
yeah. All right. So I'm going to present my work on control of flexible joint manipulators. So my name is Kimberly Oakes. I'm a fifth-year PhD student working in the electrical engineering department at RPI under the direction of Dr. John Wen. And I work in the Manufacturing Innovation Center's robotics lab. I have a picture of it to the right here. This is primarily the space robotics section of the lab. We have a granite table, which we use for simulating 2D zero-G environment. And the robot that I primarily work with is this red one on the right, which is a Baxter robot manufactured by Rethink Robotics. And it's a dual arm industrial robot that was designed for more collaborative industrial settings. So my work is motivated by robotic manipulation in space, more specifically kind of the satellite servicing type situations, like what we can see here in the top right video. So in these type of situations, what we had is a large, weak, flexible joint manipulator, which needs to move around a really large load in a robust manner. So some of the problems that this can have is when you're moving a really large load, you can have significant oscillations. And you can also have a lot of really high motor torques applied to your motors, which is a problem because typically the motors that are implemented are very small and weak to help reduce the mass of the arm that you're launching into space. So once you start exerting high torques, it's very hard for the arm to counteract those. So the goal of my work is to design robust controllers that will work for these type of arms and that will give you comparable performance both without and with this additional large load. To test my methodology, I do simulations in SimScape multibody, and for experimental testing, I use the Baxter robot. And the reason we chose Baxter is because it has joint flexibility, which you can see in this video in the bottom right. This is caused by series elastic actuators, which are located in each of the joints. And Baxter also has a pretty low payload capacity. It's about 2 kilograms per arm, and that includes the mass of the gripper. So this low payload capacity and this joint flexibility make it a really good qualitative representation for a space manipulator. So when you're designing controllers for such a system, there's a lot of difficulties, which are caused by the nonlinearity of the joint flexibility and also the resonant mode. So when you have a system with a resonant mode,
what can happen is that you can have significant oscillation at whatever the frequency of the mode is. And so when you add a really large load to the end of an arm, what you get is a significant lowering of the frequency of oscillation. So this means even slow movements could cause very undesirable performance of your system. So to counteract this, some will design controllers with really low bandwidth to help avoid the oscillation, but this also in turn causes really poor tracking performance because the response of your controller is very slow. So what I decided to do is use optimization to try and tune the controller gains so that we limit the resonant mode while also maintaining a relatively high bandwidth. So for Baxter, we have to collect experimental frequency response data because we don't have a high fidelity dynamic model. And we actually use the data directly in our controller design rather than doing a model fit because we don't have access to a lot of the low level signals that we would need to perform a traditional fit to a typical flexible joint arm model. And in addition, Baxter also has a lot of low level controllers that we don't know the dynamics of. And also because Baxter is nonlinear, we have to collect this data at a range of operating points. And this helps to ensure that we maintain the performance throughout the entire workspace. So this video is an example of implementing the controller tracking with the heavy gripper, but without an additional load. And we see that the controller has improved performance. In the bottom right figure, we can see there's less overshoot and less oscillation. So we see that the design controller has pretty good performance. Now we have tested also with an additional load on the single arm and still had the same type of performance improvement. And so for future work, we want to implement these controllers in a dual arm case and see if performance is maintained when you have the two arms coupled by a rigidly grasped load.
Thanks, Kimberly. I had a question. So when we're talking about space, what would be an application for like two arms?
So there is some interest. So the OSAM one that I showed actually does have two arms on the satellite that will be going up and servicing.
Okay. So
However, right now they're only using one and kind of just going to have the other one as a fail-safe. But there is a capability of having two arms. So it may be possible that if you use both, you have a more stable grasp and you can more easily avoid oscillations when you're transporting the large load.
I see. Thanks. The other thing would be in space, the weightless environment, how would you quantify a load? Like what's a bigger load and a smaller load in space? Is there a metric?
So that does depend a little bit on the capabilities of the arm itself, because there actually is a pretty significant number of space manipulators that have already been implemented, and their payload capacities in space actually do vary quite a bit. So it does depend a little bit on the arm capabilities themselves.
Okay, thanks. Anyone else has any question?
Tim, thank you for the.
Yeah.
Oh, okay.
Oh,
go ahead.
Go ahead.
Go ahead.
No. After you. Go ahead.
Okay. Kim, thank you for the wonderful presentation. So you said you are using optimization. I was interested in what kind of optimization problems or you formulate. Like what kind of problems do you formulate your your models?
So the problem that I'm trying to solve is actually very non-convex. So I'm actually using pattern search type algorithms to solve the problems.
Okay, I see. Thank you.
Okay. I'm more curious regarding the synthesis of the controllers. So you said that um you were so you're trying to synthesize robust controllers, but what kind of robustness are you guaranteeing?
So what I incorporate is part of the constraints in the optimization is to have sufficient gain and phase margins at each of the operating points that I evaluate at.
Okay. So for the synthesis, more or less what you're doing, some sort of loop shaping,
Yeah, in a way.
or okay. And so the so you are so the thing is that I am trying to understand the connection between this and the optimization part. So do you use any LMIs for getting the controllers?
So I do not implement those for Baxter because I'm using the experimental data directly. I don't actually do a model fit, so formulating the LMIs wouldn't be
Yeah.
feasible. Yeah.
Okay. 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 Thank you.
Excellent. Uh, Thanks, Kim. Ming,
Hi.
go ahead.
Okay. Can you see my screen?
Yep.
Okay. Hi everyone, this is Ming Yi. I'm a third-year PhD student in the ECSE department. My advisor is Professor Meng Wang. My current research interest is power system monitoring, signal processing, and machine learning. Then I'm going to introduce my recent work. The background of this research is that energy disaggregation at the substation level is challenging. Most of the measurements at the substation level are net loads. Therefore, the measurements are mostly aggregated over multiple types of loads. Besides, some of the loads, like the behind-meter solar generation, is hidden in the net point, so it is unknown to the operator. Therefore, requiring the pure measurements for each load or obtaining full labels for training are very difficult. The example in Figure 1 illustrates our problem formulation. There are three types of loads. Each column shows the aggregate data and the corresponding individual loads. These four different aggregate data are all labeled as load 3, although the other two loads may also exist. The existence of load 1 and 2 in this data are not known from the partial labels. The dictionary representation of Figure 1 is illustrated in Figure 2. Because load 1 does not exist in Figure 1C and D, the third and fourth columns of A1 are column sparse. Because load 3 always exists, A3 is not column sparse. Therefore, we will impose the column sparsity constraint over A1 and A2. The conclusion is that this work for the first time formulates the problem of load disaggregation with partial labels and offer a model-free approach with the low disaggregation error. Here is the proposed algorithm. The second constraint in equation 1 is the column sparsity constraint. The third term is an incoherence term. Minimizing this term promotes a discriminative dictionary. At the online testing stage, we try to find a linear combination from the training data. The basic idea is to exploit the repetitive pattern of loads to enhance the performance. And we use several metrics to measure the disaggregation error. And here are some numerical results. We tested our algorithm on a generated partial labeled dataset. This dataset contains three types of loads and has three partial labels. Gamma equals 50% means measurements labeled as load 1 contain 50% pure load 1 and the remaining 50% data contain mixture measurements. This is similarly for labeled as load 2 or 3. We also compare our proposed algorithm with other methods listed here, and we can see from the table 1 that our algorithm has the best disaggregation errors, which verify the effectiveness of our algorithm. We also vary the gamma, and we can see from the figure 3 that when the gamma is larger, the estimated loads are more likely to be close to the ground truth data. And that's it. Thank you for listening. Please feel free to ask me questions.
Thanks, Ming.
Mhm.
Do you have any questions?
So it is. You stated this method is framed as a dictionary learning problem. Is that?
Yeah.
Okay.
Yeah.
And so I see. Okay, it's very interesting. Thank you.
Thank you.
Excellent. Thanks, Meng. Dennis, you're up.
Okay, thank you. Just give me a second so that I can
Sure.
share my screen and start my video. Say hi to you. Okay, let's see. Hello. Okay, let's share the screen. Hopefully it's going to work fine. Okay, is it lagging or is it working correctly?
I
Can you
think
hear
there
me?
might be a bit of a lag. I can hear you, but the screen is not visible yet.
Can you see my screen currently? You cannot. Okay.
I think it's pulling up. It's just a black screen, so you might have to. Yep.
So right now it works. So the funny thing is now I have to look into my screen instead of looking directly at the
I
camera.
understand. Yeah.
Sorry guys. So let's just go with it then. Okay. So the title is Applying Machine Learning to a Multimodal Dataset. I'm advised by Professor Bülent Yener. He's a co-faculty of CS and ECSE. And if you're interested in image processing particularly, then you should consider possibly. And I'm going to first describe the dataset that we are working on and share some preliminary results. And I have a small section of tips for graduate students. And this is my 4th year, by the way. And yeah, let's start. To start with, the first part is nothing to do with electrical engineering in general. So this is the question that I receive when I tell people that I'm working on an animal model for tuberculosis. All my relatives, they say, okay, but what does it got to do with electrical engineering? Okay, I will explain that. So briefly, but let me start with the TB. So TB is a global health crisis, and each day, on average, 8 to 10 million patients are diagnosed. So it's like, yes, now we are getting used to living with a pandemic, but think of a disease that is around for longer, for way longer in mid. So TB is not like resolved. Hopefully, it will be resolved. Anyway, so our collaborators use an animal model to study tuberculosis, and that animal model is mice, a specific type of mice called diversity outbred mice. And when they give tuberculosis to these mice, what they observe is that not all of them react the same manner to the disease. And now that leads us an interesting question, because 1/3 of the mice develop early morbidity and had to be euthanized before the end of the experiment, and the remaining ones survive till the end of the experiment. So now our part comes in. We have different measurements from different modalities, such as we have the protein measurements from the lungs. We have the genotype information. We looked at the single nucleotide polymorphisms, aka like nucleobases where there is difference between in the population. We also look at the gene expression levels and the lung images. And the task is to identify patterns that can distinguish between the two classes. So you can see, for example, here, this is the 20 chromosomes of the mice, of the female mice, and you can see the different colors denote different founders. They are like inherited from different founders, and this is an example image of the lung tissue section, and this is the fancy gene expression display. This is the protein levels, and like as preliminary results in the lung proteins using the lung proteins, we have identified two candidate biomarkers, CXCL1 and MMP8, using gradient tree boosting and subset selection. And when we tested them in the human subjects, we also observed that they had some diagnostic potential. And for the SNP dataset, we are interested in developing feature selection methods to reduce to 150,000 markers across the genome to make sense of it. And then we for the lung images, we are exploring using cell graphs, which is denoted on the right. You are seeing a lung tissue section, and the brown circles, which might be not so easy to see, are the cells that we have identified using some image processing algorithms. In this case, because the cells are H&E stained, you can look at the color distributions, and you can sort of pick the purplish ones, bold purplish ones. And then the links are denoted, the artificial links that we put there are denoted by the green ones. So then now, instead of working with an image, you work with a graph and you try to do classification. Okay, so I have some general tips for graduate students that as I thought most people watching this would be like accepted students, but these tips might apply to any graduate student. And so I would recommend interacting with the PhD students in the group that you are interested in, and that would give you a sense of what would it be like to work in that group. I would also recommend using a reference manager such as Zotero. That way, instead of organizing your papers in folders and trying to sort them, you can organize them using a better interface, and you can even scrap the paper from the web easily. So I think that would be a game changer. And for me, the main differences of PhD from undergraduate is you need to do some work each day, and you need to multitask between research and taking courses. And trust yourself, you have the necessary capabilities, and check out the Troy Farmers Market. If you have any questions, I would love to answer them. Thank you.
Thanks, Dennis. I'm sure you're not the only person who's had to explain to their family and friends how their work is electrical engineering. So,
yeah,
that's true.
Unless you can fix a TV, it's really difficult to justify being called an electrical engineer.
I mean, don't try to fix it. You will break it more. So
they are PhD students, so now that's like a different category. Yeah. Okay, thank you.
Do you have any question for Dennis? Nope. Thanks, Dennis.
Alrighty. Yeah, of course. Thank you, guys.
Joe, can you go ahead and start your presentation?
Yep, just let me start my video here.
Hi, Joe.
Hi. Okay. And can you guys see the presentation?
Yeah, but we can see the presenter view.
Presenter view. Great. Let me try something here. Oh, I think I have to be in full screen before I share it. Heard this before. Right here, I'll share my screen. How's that?
Yeah, looks good.
Okay, great. So hi everyone, my name is Joe. I'm in my third year of my doctorate program in electrical engineering. I'm advised by Dr. Partha Dutta. In our department, I'm also co-advised by Dr. Narendran down the hill at the Lighting Research Center. My research is in developing phosphor-converted LEDs for circadian entrainment in Alzheimer's patients. I'm not going to talk about Alzheimer's too much just because of the time constraints, but I do want to provide just a little bit of background on the circadian system. So the circadian system is basically a biological system that governs the 24-hour rhythms of our body, and some are illustrated here. The most important in terms of my research is the sleep-wake cycle, and the circadian system is driven by this biological clock that's actually a physical clock that exists in our brain in the suprachiasmatic nucleus. And this is essentially an oscillator that it can receive input, and the strongest input to this oscillator is light. And there's actually dedicated neural circuitry from the photoreceptors in your retina to this clock in the SCN that's completely separate from the visual system. So sometimes we call this the non-visual system. And so in the absence of light, our circadian system will run a little bit long. It's about 24.2 hours. So entrainment is basically the process of synchronizing this clock and all of the associated rhythms to the solar day. So a little bit more about, what I'm interested in is developing phosphor-converted LEDs to improve circadian health. So just a little more detail about how light relates to the circadian system. It does have a phase shifting effect. And so I show a phase response curve here in the left, and in blue is the phase response curve to light. And really all I want to illustrate is that, at some times of the day, light will phase advance our clock, and in other times of the day, it will delay it. And specifically, right after you wake up in the morning, light will advance your clock, and right before you go to bed in the evening, it will delay it. And so in terms of my thesis research, trying to develop phosphor-converted LEDs, I'm really concerned about trying to improve the emission spectrum. And really what I want to do is I want to optimize the spectrum in two ways. One being trying to maximize the effect on the circadian system while still providing light, and the other being trying to minimize the effect on the circadian system. And so I'm primarily interested in this spectral sensitivity that you see at the upper right. And this is part of a model developed by the LRC that's based in the neurophysiology and neuroanatomy of the retina. And this just describes the spectral sensitivity and defines this quantity called circadian light, or CLA, which is sort of the equivalent to a luminance for your circadian system. And so my research really has two parts. The first is in optimization, and the second is in development of phosphors and phosphor-converted LEDs. And so this spectral optimization, really what I'm trying to do is optimize the ratio of circadian light to visual light, or luminance. And so this is a nonlinear constrained optimization problem. The constraints being shown in the lower right here, and these are primarily chromaticity. What color does the light appear to be, and color rendering constraints such as the color rendering index, the gamut area index, and there are a whole slew of different color rendering parameters. These are just one set that have been developed and recommended by the Lighting Research Center as part of their Class A lighting recommendation. And so really what I'm trying to do is optimize the spectrum and learn what characteristics of the spectrum are important for optimizing the circadian impact while still being constrained by these requirements for general purpose lighting. And so there are a few different approaches that we can take here that I've explored. One is I can vary the power fraction of SPDs, spectral power distributions of emitters and down converters. I can also look at more advanced models and actually add some of the parameters of those advanced models to my optimization, such as maybe the peak wavelength of an LED. And finally, this is what I call full spectrum optimization. I can split the spectrum up into a bunch of narrowband sources and optimize the power fraction of all of those sources. And what that does is it gets closer to a theoretically optimized spectrum without concern for feasibility of implementation. And so this is just briefly, these are some results from my optimization work. On the left, this is that full spectrum optimization. And really, you can just pay attention to these blue curves. These are sort of the theoretical limits that I came up with through my full spectrum optimization within the Class A lighting recommendation constraints that I showed on the previous slide. And also plotted here, I have a few commercial sources that are designed for circadian health. And you can kind of see that there is a lot of room for improvement in terms of maximizing the circadian impact. Now, these pink commercial sources down at the bottom, some of them violate my limit, but that's because they actually compromise on some of the color rendering constraints. So these would not be good sources for general purpose lighting. And then also some of the results that I've actually found for the spectrum. I've found that if I take those that full spectrum optimization and those narrowband sources, and I start to instead of using just rectangular narrowband spectra, I actually use Gaussians, and I start to increase the full width half max to sort of smooth out the spectra a little bit. I start to see that that I have a few emission bands that form, and interestingly, these emission bands are pretty close to the same regardless of the correlated color temperature. And so these are the areas that I'm concentrating on for phosphor development, for improving improving the high CLA sources. And so finally, I just wanted to, this is something that I haven't made as much progress on at this point, but I'm also working on experimental phosphor synthesis. And I'm currently looking at cyan phosphors because there aren't a lot of these that exist right now. And certainly, well, all phosphors have, you have to think about stability and things like that. But I'm specifically looking at trying to find narrowband down converting phosphors. But I just wanted to show, this is kind of what I deal with in my lab in terms of phosphor development. We do solid state synthesis. So we grind up precursor materials and then put them into this, we use a big tube furnace to heat these up so that the materials decompose and then the elements can diffuse and create our matrix. And then by adjusting the ambient that we use, we can activate our rare earth dopant in order to create the luminescent centers. And this in the center is just an example of a phosphor that we've developed in the past year. This is a strontium thiogallate that emits in the green. And that's all I have. Thank you.
Thanks, Joe. Interesting stuff. So if I understood correctly, a lighting source based on your optimizations, that would probably be a compound source with different types of LEDs or same type of LED with different phosphors, right?
There actually are some people working on dual pump. There are actually some commercial dual pump sources that have multiple LEDs. From the optimization perspective, I was kind of just describing different approaches. For my specific goal for my thesis, I'm looking at using one LED pump, and then I'll use a blend of phosphors to create the phosphor converted LED. So I'll have multiple down converters.
I see. Okay. Cool. Do we have any other questions for Joe? Excellent. Thanks, Joe.
Thanks.
Thank you for your presentation. Barak, are you ready?
1 second. Okay, I believe you see my screen, but do you see it in full screen now?
Yes.
Okay, great. So, hi all, I am Burak Varıcı. I'm a third-year PhD student working with Professor Ali Tajar. I went a bit lazy with the slides, and I'm relying on my some recent presentation for our recent paper. So mainly I'm working on the structural learning in high-dimensional regime, both directed and undirected, and I am specifically more interested in the structured learning in the existence of multiple models. And today I will briefly talk about our work on the learning shared subgraphs in Ising models. So the probabilistic graphical models usually are used to describe complex dependency structures in various domains. And actually in these various domains, we face multiple information layers with the existence of especially different sensing technologies. For instance, different brain imaging techniques may result to different data for the same underlying phenomena, and each one can be represented with a distinct graphical model. Or similarly, some molecular structures may have some shared substructure that can be useful for drug discovery to reduce the search space for a new drug, let's say. And that's why learning the shared subgraph of the existing multiple models for the same underlying phenomena is helpful because it gives the most reliable information about the situation to us. And that's our motivation basically to study how can we learn the shared subgraphs of two graphs given from represented with basically two different data distribution efficiently. So in general, structural learning refers to just observing some data from the data distribution and estimating the underlying edge connectivity. And here we are considering the undirected graphical models. And the shared structural learning can be formulated as observing data from two graphs and estimating their basically the intersection of E1 and E2 edge structures. One can naively learn basically two models separately and form the shared estimate afterwards. But once we are only interested in GS, which is only interested in the shared structure, this is very inefficient because let's say I have a huge model, and as I mentioned, we are mostly working within high dimensional regime. I may have a huge number of random variables, which I am only interested in a small shared part of that, shared over two graphs. So our aim is to estimate only that part without learning the whole graph. And this will save us, basically this will result in significant savings in the needed samples. And we are using Ising model in our simulations and studies, which is a pairwise binary graphical model, basically, where each each xi random variable is taking values either -1 or +1. And we are basically characterizing this goal with a graph decoder that maps data from two different models and maps them to a shared subgraph estimates with the aim of exact recovery. And as I mentioned, the sample complexity here is the key. We want to basically we want to need at least least possible amount of sample observations, the vertex observations that we need from the system. And that's how we characterize the sample complexity, basically number of total observations we require from a system. And we devised an adaptive algorithm focused on learning the GS, and it has two steps. Let's say we have two models, and here basically the green parts are corresponding to the shared subgraph that we want to infer given the data from the first model and the second model. At each iteration, we have a pruning step, which basically forms an estimate of the nodes of interest that we want to learn their internal structure of the VS. And at the second step, we perform basically we perform some joint learning updates to learn these internal structure. And gradually, these VS estimates will be getting better, and our joint learning will learn faster than learning these graphs individually. To see a bit more how it works, at each pruning step, we form some coarse estimates of the underlying shared subgraph using the pairwise empirical means. And importantly, this narrows down to sampling to only our nodes of interest gradually. And in correlation decay regime, this is guaranteed to yield the exact shared node set Vs. And then later, we use a joint multiplicative updates algorithm. Basically, it is similar to Hedge algorithm, which is usually used in some related problems, basically multiplicative updates. However, instead of using one loss, we are just combining the loss from two models to perform the joint updates. And this accelerates the learning significantly. And one problem for the theoretical guarantees is that the joint PMF of these random variables is basically finding a closed form is quite difficult and intractable besides some simple cases. And that simple cases I refer to when GS is isolated and if our pruning step works correctly, we have the sample complexity guarantees such that our joint learning algorithm will have these now, like don't put too much emphasis here, but I just want to notice the Q and P here, the scaling behavior. Here, our joint sample complexity scales with log Q, that is size of the shared subgraph, which can be, as I mentioned in the beginning, much smaller than the whole size of my problem, whole size of the graph. If I were to perform independent learning, then I would need to inevitably have a scaling behavior with log P. This is basically the contribution in terms of sample complexity. And in simulations, I put here the synthetic data simulations. Basically, we take some Erdős-Renyi random graphs in 200 vertices to be in the high dimensional regime. And we compare our method against several state-of-art baseline approaches where individual graphs are learned. And we outperform both of them significantly. As a real example, I didn't put it here, but it can be used in let's say Ising models, since they are binary models. It is a good choice for the human behavior modeling. For instance, there exist some studies which also we compared our works against is human behavior modeling of the US Senate vote data, basically. And since we have, let's say, it's a bipartisan behavior is usually observed, you can basically from the data build the graph and observe the formation of the smaller subgraphs which are shared, let's say, between two political parties, even though in general they differ. They may have some similarities for certain topics, and then you can infer it basically from the model. And this was basically what our paper talks about. More recently, I didn't put it in on the slides, but I am working on the causal structure learning on basically in similar type of problems, but instead of learning the shared substructure for causal networks, it is usually more important to learn the difference between two graphs. Like in general, two graphs may be similar to each other, or let's say I may have one graph, but I can apply some intervention to the system, which cause some changes in the model structure. And I'm trying to learn those changes as quick as possible, or with as least number of samples as possible. And that's basically that's how my research is evolving around. Do you have any questions?
I have one question. Can we go to the first slide or the second one, like where you display the graphs?
This one or this?
Oh, yeah, this one, yeah.
Okay.
So, like, can you describe again, because I think the work is very interesting. I just want to get a sense of what the distributions are. So we have X1 corresponding to a particular, like in the case of the partisan example, like, can you make the analogy?
Okay,
like...
yeah. For the partisan example, let's say my random variables 1 through 100, let's say 1 through P are the senators in the Senate.
Mm-hmm.
And let's say, and each data sample corresponds to voting on a let's say bill. They can be either like yes or no, -1 or +1. So that for each new bill, I have one data sample. But I can, let's say, I can consider the accepted bills or the rejected bills. We can think that those two would need to have probably different data distributions. Let's say one will be dominated by, let's say, for some bills, okay, how to explain it? Let's say if one political party is in the majority, then they will most likely pass the bills that they want, and the ones they won't pass. So that the rejected bills can be considered as F1, one data distribution, and the accepted bills can be considered as another data distribution, F2. And once we basically learn an underlying model, they will be different.
Okay.
And, let's say you can think that the same political party would have same model in both graphs, in both data distributions, but actually it relies on the topic. Let's say it relies on the domain. Let's say for healthcare, they may have different opinions, and even within the same political party, they may not be shared over two graphs. But in, let's say, some military spending, they may have more conservative, more closer views to each other.
Yeah, okay, great, thank you.
Okay, thanks for asking.
Thanks, Barak. So we have one more presentation. I know we're a few minutes over the time. So my colleague Esten, who was supposed to give the presentation, he was sadly not able to make it, but he did record a presentation for us. So I'm going to share that presentation.
Makwi, and I will be summarizing my PhD research today.
Can you hear the presentation?
My ongoing research has We have worked on developing a rapidly deployable, energy-efficient power control strategy for demand response amenable hydronic HVAC systems in buildings. We have studied workspace thermal management using heterogeneous heating and cooling elements. Finally, we are also working towards energy-efficient indoor air quality management in buildings. I will now provide an overview of the first research direction while giving a brief background of the keywords in green. Demand response refers to changes in electric usage by consumers in response to high use periods to decrease demand on the grid and maintain electricity reliability. The consumers are paid for signing up for such programs. Since modern buildings usually do not instantaneously become too cold or too warm, their heating and cooling systems appear to be suitable candidates for offering demand response by allowing indoor temperatures to float between certain upper and lower thresholds. In this work, we focus on hydronic HVAC systems. These systems involve the circulation of heated water around a building. The heated water transfers its heat to each room through heat exchangers. The water's temperature is lowered and is returned to the boiler for reheating. A similar process involving cooled water and a chiller can achieve the cooling operation as well. Our work aimed to minimize energy costs incurred by the consumer that is enrolled in a demand response program subject to operational and thermal comfort constraints. As is obvious from this diagram, thermal management using the hydronic HVAC system would involve controlling several operational variables such as the return temperature and the mass flow rate of water. Through our studies in this domain, we were able to significantly reduce the dimensionality of the problem by expressing the entire framework in terms of the power required to heat up or cool down a room. We simulated the results from our mathematical formulation for a typical multi-unit demand amenable building and observed that our strategy successfully reduced energy costs by pre-cooling the space prior to the onset of higher price intervals. This pre-cooling operation is characterized by brief increases in power consumption as marked by the red ellipse. The next research direction is workspace thermal management using heterogeneous heating cooling elements. To this work, we developed optimization frameworks for time-bound pre-cooling, preheating, of a workspace in preparation of, for example, a meeting, and for achieving spatial differentiation in the thermal environment. The frameworks used learning techniques for determining the thermal parameters of the testbed and modeled predictive control to make the approach robust to changes in ambient conditions and imperfections in the thermal model. The testbed for our experiments was the smart conference room at the Lighting-Enabled Systems and Applications Center here at RPI. The room is equipped with 3 heating elements and 1 cooling element. It may be observed that our energy-efficient pre-cooling, preheating operation successfully achieved the desired temperatures at the end of the 60-minute deadline by determining the latest instance by which the HVAC elements needed to be turned on to achieve these temperatures. The plot at the bottom shows how for separate test runs we were able to achieve a spatial temperature differentiation of close to 1 degree Celsius, which could be instrumental for achieving a more personalized work environment. The third direction deals with energy-efficient indoor air quality management in buildings. Through this study, we aim to determine how we can modulate the fresh air supply to the building and the mass flow rate of air to individual rooms to maintain the desired temperature and the indoor carbon dioxide concentration within permitted bounds, while remaining energy efficient and robust to changes in room occupancy levels. This study is in progress. I thank you all.
So since Essen unfortunately cannot join the meeting right now, if you have any questions, please reach out to the Graduate Student Council and we will connect you with Essen. I would like to thank all my fellow graduate students who took the time out of their schedules to give presentations about their research work, and to the accepted students who joined the call. We would make this recording available on our website, so if you missed it or you want to go back and look at something again, it would be available. Thank you so much. Have a good day.